first of all, I think the most significant changes are in the hardware, not in the software.
Mm-hmm.
Right? I mean, when the first machine I used, the IBM 650, it filled a huge room, and the three things in my pocket today are more powerful. Each one of them is far more powerful than that room full of equipment. Another thing, just about the technology, I actually, around the early 1970, invented Windows. I mean, not the operating system Windows, I mean the idea of having Windows.
Hi. Good morning.
Good.
Well, good
afternoon.
Yeah, almost good afternoon. So we are at a conference in Belgrade, and I'm wondering, how did you like the conference so far?
Mixed feelings.
Mixed feelings, yeah?
Yeah.
What are those mixed feelings?
Well, I heard some good substantive talks.
Mm-hmm.
And I heard some where people were just talking to be talking.
That happens sometimes.
Yeah.
Did you have a favorite talk so far?
Oh, mine.
Okay. And what was your talk about?
It was about how software gets old and how to keep it from getting old. It's a topic that's very close to my heart as I get older.
Mm-hmm. You have been in the industry for quite a long time. How long was it?
I'm trying to think, but I wrote my first software around 1959 and 1960.
Okay, so 1950s and 60s. And what kind of machines you were working with in those days?
The first machine I used was an IBM 650. I also used about the same time a Bendix G15. I'm not sure which one was older.
Mm-hmm.
Neither machine is anything anybody today knows about.
Yeah, I mean, most people don't even think about how this whole industry got started, right? When I was a kid, my mother used to bring home these punch cards because sometimes they would screw up the punching, and then they just took it home. And I was drawing on those old punch cards.
They were also good for shopping lists.
Yeah, I can imagine that. And the machines you were working were they more like punch card machines, or you already had some kind of magnetic tapes in there?
In both machines when we started, we had punch cards.
Mm-hmm.
Some machines around the same time were still using paper tapes, and the paper tapes taught you where the word patch came from, because they used to actually change a program by taking a little glue and a little piece of paper, papering it over the hole, and then punching another hole somewhere else, and that was a program patch.
That's an interesting story. I didn't know that.
I watched someone do it. I never did it myself.
Okay, that's really interesting. I didn't think of that ever. Like, I knew that the first modularity was like stacking different colored punch cards on each other. That was one of the dirty tricks back then, but I didn't know this patch.
That's something I didn't know. So
really,
now we're even.
Yeah. So the thing is, my mother used to bring home like 3 different colors of these cards, and then when I asked later, when I was already a software developer myself, why did you have these different colors? It turns out what they did was they had each method was in a different color, and then the way they would assemble the program was they just put different colored stacks on each other, and then the whole stack went into the machine, and when they finished, then they resorted according to colors, so they didn't have to look at it manually where the method starts.
Maybe that's a Hungarian secret.
Oh, well...
You saw your mother do it, but I never saw it, but that just doesn't mean much.
Yeah.
Because, in fact, that was a big problem. I remember putting some ink on the top of key cards, so I could find things in the...
That's another solution, yeah. So that other solution with the colors, it's a bit problematic because you actually had to punch each method in 3 different colors so that you can always find a different color for the next method, right?
Yeah.
And what do you think? What were the most important changes during the years? So you have first when you started, you had, I guess, procedural programming and stuff like that. What were the major milestones for you as you were working?
Well, first of all, I think the most significant changes are in the hardware, not in the software.
Mm-hmm.
Right? I mean, when the first machine I used, the IBM 650, it filled a huge room, and the 3 things in my pocket today are more powerful. Each one of them is far more powerful than that room full of equipment. Another thing, just about the technology, I actually, around early 1970, invented Windows. I mean, not the operating system Windows. I mean the idea of having Windows. But I'm going to tell you why it's the stupidest thing I ever did.
Okay, and that's interesting for me.
Yeah, because I was working at a terminal, and I had piles of paper, and I was looking here and copying something, and looking there and copying something, and I had to refocus my eyes and find a thing in the paper. And I said, why can't I divide my screen into windows? Mm-hmm. And then I have different files in there, and I can cut and paste. I had all those ideas. So I did what any academic would do. I first formally defined this idea. Mm-hmm. And I actually have published a paper about a Windows interface with a formal definition, a very early, primitive kind of formal definition. And then I gave it to a student, which is the second thing you do in academia, is to get somebody to do the grunt work, and usually a student. And this was a very good student. He took the specification, went away, came back a couple months later, and said, I finished it, it works, and you're not going to like it. And I said, why am I not going to like it? He said, well, because I'll show you and you won't like it. So I went and he showed me. And as soon as I saw the first part of the demo, I knew what I was wrong. Because the terminals we had at that time were what we called glass teletypes. That is, they had a screen, but they worked like a teletype machine. So they wrote characters on the bottom of the screen one at a time, and it scrolled up the way a piece of paper would scroll up. Mm-hmm. And they wrote the characters at 15 characters per second. And any time in my thing where I change anything in any window, it had to rewrite the whole screen.
Okay.
At 15 characters a second.
Okay.
So you would make a change, and then you would go out and get some coffee and come back, it would be almost done. So he was right, I didn't like it. And this was an idea that was clearly ahead of its time, because the hardware wasn't up to it. Mm-hmm. But I mean, there's really nothing new in the software world. The theory was always the same, but the hardware has gotten better. So now, routinely, we do things that I thought were a great idea. At that time, I've since learned, there were people in California who had the same idea, but they had very expensive hardware that allowed them to do random access to a screen. Mm-hmm. Yeah. So theirs was much more useful than mine. And of course, they didn't quit. I quit. So,
yeah.
But it's a good lesson why you look and say, it's not the software that's new, it's that the hardware makes it work.
Yeah. Mm-hmm.
I hear a lot of old ideas when people talk about software, but I know that they are old, whereas now they work and then they didn't.
Yeah, and it's interesting because also what I seem to see is that sometimes ideas just come back, right? One of the things that we just talked about before we got into the car is neural networks, right? So that those were around pretty early on. It just wasn't really practical at the time, and I think they are practical for certain purposes by now. You seem to have a different opinion on that.
No, I have a different standard.
Okay.
You see, I began my academic student life as a physics major, and then changed to engineering. And the person who convinced me to change tried to describe the difference by telling a story, which was about the reinvention of what we used to call a variac. Now, he was, as an engineer, invited to visit a lab in New Jersey, and as part of a committee to evaluate the work of the lab. And when the people at the lab heard that he was there and that he was an engineer, they said, "Oh, you're an engineer, we'll introduce you to our engineer." So he met this guy, and he wasn't an engineer, he was a physicist. And he asked, "Why do they think you're an engineer?" And he asked him, and it was because he had built a transformer with controls on it so that you could vary the ratio between the voltage in and the voltage out. Okay. And he had a very primitive thing, a big box, and you could then use it with these levers and move the thing around. What he didn't know was that there was already such a device on the market. It was called a variac, and it was neatly packaged, had a little knob that did the job. And his colleagues, who were physicists, were very impressed because he built something that had worked and was useful. Okay. But the engineer was always asking, is there a better way to do it? So when you talk about neural nets, you're very impressed by, well, they can do interesting things. And I asked you the question, is there a better way to do it? That's the engineer's question. And what bothers me about AI in general and neural nets in particular is not that people are having fun playing with them, but that they are proposing that they're a good way to solve a problem. And they're saying that you can make practical tools that way. And I don't think it's ever the right way to make practical tools.
Okay. Well, I'm not sure, because there are tools that are already out there and quite practical, like cancer detection, which you can double check it, right? So it's not like you have to be right all the time. But on the other hand, it's really useful for checking, to do a pre-check by a machine and make the medical professional's job easier.
Well, but there are many ways to do that. I mean, that's the same discussion we were having at the panel session yesterday. You can do all kinds of things. Maybe, first of all, I think there are almost always better ways to do that kind of thing than to use the AI approach. And sometimes you want a better way. I have an article that talks about a very early example where somebody I knew, a very smart guy, wrote a machine that could play penny matching. You know, the game where you put a coin down and one person wins if they're both the same. Two people play and they put the coin down, and if you get heads, one person wins, and if it's both, if they're different, the other person wins. That kind of a game. And he built this little box. There was no software in it that was beating people everywhere. And he was doing this, it turns out, to try to show how stupid the usual interpretation of Turing's work is, because it took no intelligence at all to beat people at this simple game. But the other thing about it was, the minute he explained how it worked, you knew it wasn't intelligent and you win. You knew how to beat it. And with a lot of these methods, if you know how it works, you win. I read another article that had a test from the suitability of a woman to be a mother by testing the hair, because they discovered a lot of bad mothers had alcohol traces in their hair.
Oh, okay.
Right? And then it turned out there have been now a number of cases discovered where the mother didn't drink at all, but she used a hairspray with alcohol traces in it.
Okay.
Right? And that kind of thing is very dangerous and damaging to people. So you want to trust your tools to be something you can at least prove that they're reasonably correct, and that there are no cases where they will have disastrous results.
Okay, but what about the case where you use the neural net approach to come up with the algorithm. But then after that, you kind of debug it and try to understand what's going on behind it. Because that's something that happened with image recognition, where they first had the VGG network and no one really knew what was going on. And then they started dissecting it and understanding what each neuron was doing. And once you have the algorithm, it's easy to figure out how you would write it by hand, after all.
And how you could write it better.
Well, not necessarily. You don't always find a better way that way. In that case, they did. They actually come up with another neural network, the Inception, which was actually based on the learnings of what they did with the VGG.
But I bet if they showed that then to somebody who didn't believe in neural networks and just wrote code, he would do it better yet. Especially if he was from the area of signal processing, because a lot of the ideas in the AI type of image or character recognition software are very old areas in the area of radar. They use it to identify planes, to detect planes, things like that, to get rid of very noisy data, radar in a military situation. And they have very sophisticated mathematical algorithms for doing that. And they're often far better than the ones the AI people invent. But the AI people don't look in the literature from radar processing.
I don't think they do, because
I've interviewed some. I've interviewed some. That's how I know this example. We interviewed a new PhD who was very proud of what he had, but some people in our department were radar experts, and they pointed out how primitive it was and how much better they could do with mathematical algorithms.
Okay.
So, even today, you were talking about how they use convolution in some of those algorithms.
Yeah.
And in fact, I learned about convolution as an electrical engineer for signal processing. It's not a new idea, and I'm willing to bet the algorithms I learned, or the ones they use now in that area, are better than the ones that you found. Simply because they've been studied for more years and there's more math applied to them.
So the way I look at AI is its tool for solving problems at some level, and maybe at some point you will come up with a better solution, but even then it might give you great ideas on how you approach the problem.
If you use it as a research technique, let's say, I'm out of ideas, let's see if a neural net can do it. Okay, but if you deliver that as the final product, it's not. I have another article in the Communication ACM a few years ago called The Risks of Stopping Too Soon. And you look at many of the things people do. In that case, I was talking about requirements analysis. They get a big list of statements, but they never get a real full statement of requirements. They just have a whole lot of wishes. It's a wish list approach. Now, if they make the wish list approach and then they start trying to translate that into a sound complete specification, then I'm happy. But if they stop with the wish list approach, there's always something that's left out. There's no way to test those for completeness. There's no way to test them for consistency.
But you can iterate on that, right? So even if you don't get everything right,
you never know when you're done, because there is no mathematical tool. Whereas the documents that I write have very simple mathematics for telling if you're done or not. It doesn't tell if you're right, but it does tell if you're complete and consistent.
Yeah, but so where I see a collision there is that most of the time in practice you are not interested in the perfect solution. You are interested in the sellable solution, right? So in many cases it's acceptable if something doesn't do everything right the first time around. What you want is to test if the market is at least interested in what you are doing, and people are, especially early adopters, are willing to put up with a lot of errors in return for having a early glimpse of what's coming, right?
But now we're back to the original philosophy, whether you're an engineer or a salesman. Some of the things we were talking about earlier, why my standards for whether something is good or not are different from yours, simply because I was trained as an engineer then before I bring a product out. My first concern is that it do its job, not that it sell. Then there are other people that have to ask about the sales. I may do both jobs if I have a one-man company, but I never forget that the biggest concern is not to sell something that's dangerous or inappropriate or incomplete. So.
Yeah, well, what I see in the industry currently, and that's really just my experience, is that most of the time when a company starts, they have very limited funding, so they end up doing something good enough that they can test on the market, because if you do market research without the actual product there, it's probably not going to give you the same results as if you show something half-baked in some sense. And then when you already know what's worthy of developing full scale, then you can get funding for a more complete solution.
I think the trouble with that is to think about something like Samsung and its batteries. Samsung did itself a lot of damage by trying to be the first to market with a battery that was that big and that light and so forth, and not testing it for whether it would explode or not.
But that's a different story, I think, because there you know that there is a need. And I don't think it's a worthy goal to be first to market with a product that is dangerous, and especially in the case where you actually know that if you build that thing, then there will be a need.
Well, I'm not sure that they knew. You know, maybe it, like the AI thing, surprised them. I'm sure they didn't send it out believing that there were going to be explosives on the plane and things like that. No, I'm just saying, I understand the pressure to go to market, but what we taught in engineering school, and what we were taught, and what I have always taught, and because I've been a professor of engineering, is that your first obligation is to make sure that the product is fit for use. And then you start saying, you know, does it sometime is not a criteria that's good enough. It has to do it all the time, or at least you have to be able to say when it'll work and when it won't. And that's not what I see being done in AI.
Well, it's probably not done for every product. I do know that for some products there is a great need for that. I mean, one example being the medical use cases where you don't want to make too many mistakes, right? Because people might die, and in those cases, it's actually really important to understand the results of what the AI did.
Well, there is an argument on your side for medical cases that if you do something that saves a life 1 in 10 and otherwise all 10 would die, it might be still better than doing nothing.
Yeah.
Right? So I see those arguments, but I still believe you can do better. One of my colleagues back in Canada once did a nice demonstration. He had the head of our laboratory was a very big fan of neural nets and written several books. Even though he was a radar engineer, I thought he'd just gotten old, but and maybe he didn't get old, but he's still even older now. But anyway, he was talking about how he could solve this problem, and my friend Sanjing Chao just took a least squares algorithm and did it better. And least squares is one of the oldest mathematical methods used in that kind of job when you're trying to optimize or fit something.
Which one was your favorite machine you worked on over the years, and why?
Always the one I have now.
Okay, that's a good philosophy.
Well, they are so much better today than what I could. Each one is so much better than the last one. I mean, now if you're buying computers, they're a consumer good.
Yeah.
They come with specifications that tell you roughly how fast they are.
Yeah.
They come with ratings in consumer magazines. You can try them. There's no need for anything like that. So, for me, if you ask what was my happiest discovery, it was when I discovered how useful mathematics could be in what I was doing. I knew that from my electrical engineering work, and then I got into software, and I didn't see anybody using mathematics. And then after a while, I got into really complex software, and I needed some help, and I found the mathematics that I'd learned as an engineer could be adjusted to be suitable for what I was doing. And that was my happiest surprise, that all the things I learned in school were still useful.
So thank you for being on the show, and I really enjoyed the discussion.
Thank you for the tour of Belgrade.
Yeah.
And the discussion.
Okay. So thank you very much. I still have to find a parking spot, so...
You need an AI for that.
Yeah, sure. That would be a good idea.
That's the one thing I'm hoping for from AI.
Okay.
And actually, I don't think the right way to do it is AI. Look at the airport in Frankfurt, Germany. You can find parking places without AI.
Yeah. Okay, thank you. Goodbye. Thank you for watching this episode of The Morning Commute. I hope you enjoyed it and maybe it earned your subscription. If you would like to meet me this year, there is going to be plenty of opportunity because I'm going to a number of conferences. First, in March, I'm going to go to Vienna to the Vox Days, where I'm going to do a talk called Learning to Fall. It's about how you can build a service that relies on other services to achieve a complex scenario and make sure that this service is still resilient even if those other services fail sometimes. After that, in April, I'm going to go to the INAT conference in Belgrade, where I'm going to talk about how you can protect your engineering culture, even if your company is hiring a lot of people. Essentially, we set up a bootcamp for new developers, and I'm going to talk about how this bootcamp was set up and what kind of results we had with it. In May, I'm going to do a workshop at the Craft conference in Budapest. It's going to be about delivering value early and often, which is, I think, very important, and it's the cornerstone of agile practices. We are going to build software and make sure that we have quick feedback loops using continuous deployment and lean startup techniques. If you know about Lean Poker, this is essentially going to be Lean Poker. After that, in May, I'm going to go to Cluj in Romania to the Dev Talks conference, where I'm going to do the same bootcamp talk as I did in Belgrade. And also in June, I'm going to go to Bucharest to do the same talk at another Dev Talks conference. So it would be lovely to meet you at any of these conferences. So I left links in the description to all of them, and you can pick and choose, and maybe we can meet in person. And if not, then, well, see you next time on this channel. Bye.